Dear students, today I want to discuss the very important topic rigid body dynamics or rotational motion. In the last examinations, this chapter became very important. For NEET and KEAM entrance exams, we can wait more than 3 questions, and for JEE minimum 2 questions. So at first, keep in mind one thing: the important factors relating to circular motions are applicable for here the rigid body dynamics. And keep in mind, the circular motion in the sense have to deal only the particles, but here n particle systems. So at first we can just compare between the linear motion and the rotational motion, especially the kinematic relations. In place of displacement, velocity and acceleration in linear motion, here the terms angular displacement, angular velocity and angular acceleration. And keep in mind, in linear motion, such vectors are called as polar vectors, but here the theta, omega, alpha, etc. are called axial vectors. Here, the linear velocity is the first differential of displacement as dx by dt, but here the angular velocity is d theta by dt. The linear acceleration, we can express dv by dt, the variation with respect to time, but with the distance we can express as the velocity into dv by dx. It's a very important relation. But for rotatory motion we can say as alpha equal to d omega by dt or equal to omega into d omega by d theta. So it implies v equal to u plus et, omega equal to omega 0 plus alpha t. And keep in mind here the alpha, the angular acceleration, omega, the angular velocity after a time t, and omega 0, the initial angular velocity. The displacement after a time t in linear motion as s is equal to ut plus half it square. But here the angular displacement after a time t, that is equal to omega 0 t plus half alpha t square. We can relate the final and the initial velocities with the displacement as v square equal to u square plus 2s. Here omega t square equal to omega square plus 2 alpha theta. The displacement in the nth second as u plus a by 2 into 2n minus 1. But here angular displacement in the nth second as omega 0 plus alpha by 2 into 2n minus 1. We can go with some problematic situations. Then we can get the concepts so clearly. A wheel is rotating with angular velocity 2 radian per second. It is subject to a uniform angular acceleration 2 radian per second square. What angular velocity does the wheel acquire after 10 seconds? How many revolutions will it make in this time interval? We know the angular velocity after a time t is omega 0 plus alpha t, the direct substitution. So omega 0 becomes 2, so 2 plus 2 into 10, you get that value as 22 radian per second. We can find easily what is the angular displacement after a time t. Simple equation, omega 0 t plus half alpha t square. We get the answer as 120 radian. But keep in mind, if a particle undergoes one revolution, it makes an angle of 2 pi. Then for the total displacement, for n revolutions we can write as 2 pi n, the very important concept. So we can find the number of revolutions is equal to the total angular displacement by 2 pi. Approximately you get the answer as 19. A good question. A flywheel rotates with a uniform angular acceleration, its angular velocity increases from 20 pi radian per second to 40 pi radian per second in 10 seconds. How many rotations it undergo in this period? And here we can easily find the angle theta as omega t square minus omega 1 square by 2 alpha. And here the angular acceleration we can find easily as omega t square minus omega t minus omega 0 by t. You get the value 2 pi. You can just substitute. You get the value 300 pi rad. But we know the angle as 2 pi n, and we get the value n is equal to the number of rotations is equal to 300 pi by 2 pi. We get the answer as 150. Another good question, a particle starts rotating from rest according to the formula. Here the angular displacement is expressed in terms of time. We have to find the angular velocity and angular acceleration after 5 seconds. The easy method, omega, the angular velocity is the first differential of angular displacement. You just differentiate. So t cube we can differentiate to be 3t square. T square as 2 into t. So by putting the value t equal to 5, so you get the answer. Then we have to find what is the angular acceleration. Once again we can differentiate. So 9 by 20 into 2t minus 2 by 3. By substituting the value t equal to 5, you get the answer. Good question. A very important concept. A rigid lamina is rotating about an axis perpendicular to its plane through a point as shown in figure. The angular velocity of the point B, in the figure it is given, it is rotated with an angular velocity omega. But keep in mind, in a rigid body, the angular variables remains constant. The only change happened to the linear variables. It is a very important concept. We can wait one question from this area, moment of inertia. Very, very important concept. And keep in mind the resistance offered by a rotating body against the change of state. For a single particle, we can say as I is equal to m into r square, the mass into the square of the perpendicular separation between the particle and the axis. But we can say for n particle system, it is sigma mi ri square. We have to considering all the mass particles constituting the body, and we have to consider all the perpendicular separations. But for an extended object, suppose a small mass dm is at a separation r, and we can say that moment of inertia take the value as integral r square dm. And keep in mind the moment of inertia depends upon the three factors: on the mass of the body, the mass distribution of the body, and the position of axis of rotation. And keep in mind it depends upon the size and the shape of the body. But it does not depends upon the angular velocity, angular acceleration, torque, and angular momentum. It is a very important concept. And we can go through some problematic situations. A good question is waiting. Find the moment of inertia of a rod about an axis inclined at an angle theta with the rod and passing through one end. See, to solve it, and we can just assign a small element dx at a separation x from the axis, but with respect to the axis, the perpendicular separation is r. So our formula is I equal to integral r square dm. So r is the perpendicular separation, but here the relation with x is needed. So we can just relate that r and x by using the sine theta. So you can substitute that r square is equal to s square sine square theta. But dm, it is in mass, so have to convert in terms of this dx in length. So for that you can use the concept as the linear density. So that is dm by dx, that is equal to capital M by capital L. So you can substitute in place of dm as m by L into dx. So m by L into sine square theta into integral x square dx. We can integrate as s cube by 3. It's a good question. You get the answer as ml square 3 sine square theta. 4 bodies of masses 5 kilogram, 2, 3 and 4 kilograms are respectively placed at positions 0, 0, 0, 2, 0, 0, 0, 3, 0 and minus 2, 2, 0. Calculate the moment of inertia of the system about x, y and z axis. But keep in mind, if it is along the x-axis, okay, fine. The particles along the x-axis have no contributions. So we have to analyze only the 3 kilogram and the 4 kilogram. And the 3 kilogram is at a separation 3 and the 4 kilogram at a separation 2. You get the answer. 3 into 3 square plus 4 into 2 square. But if you just considering the y-axis, again, the particle along the axis, because of there is no distribution, so there is no contribution to the moment of inertia. So we have to consider there is only 2 contributors, one because of 2 at a separation 2 and another one 4 at a separation again 2. So you get the answer as 24. Then what is the contribution from IZ? So the axis is like this one. So we have to consider the 3 contributions, and here the 2 is at a separation 2, the 3 is at a separation 3. Then what about the separation from 4? The perpendicular separation is needed, so that is the diagonal here. So that is nothing but here it is 2, and hence this perpendicular separation become 2 root 2. So you can just find the value. But there is another concept. We can just jump into the perpendicular axis theorem. You know that IZ take the value equal to Ix plus Iy. We can verify here. 43 plus 24, it is 67, a good aspect. But keep in mind that the theorem is applicable only for laminas, 2-dimensional objects. We can wait another question, a good question, a previous year concept. The 2 masses, M1 and M2, are placed at a separation r apart. Find out the moment of inertia of the system about an axis passing through its center of mass and perpendicular to the line joining the masses. Look the figure. The 2 masses M1 and M2 are at a separation small r in total. But we can just assign that center mass is at a separation r1 from M1 and r2 from M2. So simply we can say the total moment of inertia is equal to the sum of the individual contributions. The M1 contribution we can say M1 r1 square plus M2 r2 square. We can substitute for r1 is what? R1 is nothing but r2 by the total mass into the total separation, that much square, plus M2 into, how we can find the value of R2? That is R1 by the total mass into the total separation, the whole square. So you get the concept as I is equal to M1 M2 by M1 plus M2 into R square. But keep in mind the concept that M1 M2 by M1 plus M2 is called the reduced mass of the 2 particle system. That means that 2 particles will give the same rotational effect if they are replaced by a single mass particle at a separation r from the same axis. You should know the parallel axis theorem, and that theorem is used to find if we know the moment of inertia along the center of mass axis, then we can easily find the moment of inertia about any parallel axis at a perpendicular separation A, and that is ICM plus M into A square. A lot of applications are waiting. The perpendicular axis theorem, keep in mind, as we already said, it is applicable only for the 2-dimensional objects. And here, a plane lamina. And if you just know the moment of inertia of the plane lamina about the x and the y axis, then the moment of inertia about the z axis is given as Iz is equal to Ix plus Iy. But keep in mind that x, y and the z must pass through the center of mass. But there is an exceptional for symmetrical bodies. Symmetrical bodies are like a ring or a disc. For a square, that two axes need not be perpendicular. That ix and iy need not be perpendicular. The radius of gyration, it's a very important one. We can replace a bigger body by a point particle by placing at a radius of gyration. So we can find the moment of inertia of a body if knowing the radius of gyration by just multiplying the mass with the square of that radius of gyration. It will give the moment of inertia. And keep in mind, it has no meaning without the axis of rotation. And keep in mind, it is a scalar quantity. Look here. The radius of gyration for an n particle system can be easily find out as equal to root of r1 square plus r2 square plus etc. rn square by en. It's a good formula. We can go through some important concepts. The radius of gyration depends upon the axis of rotation, the distribution of mass, but not depends upon the mass, not depends upon the angular displacement, angular velocity. And keep in mind, for symmetrical separation, for symmetrical attachment, keep in mind K remains unchanged. But for asymmetrical separation and asymmetrical attachment, keep in mind it depends upon that K will change. That is a very important concept. For asymmetrical separation and the asymmetrical attachment, that K will change. It is a very important concept. We can go with some important concept. Four rods are arranged in the form of a square. Calculate the moment of inertia of the system of the rod about an axis passing through the center and perpendicular to the plane of the square. So that four rods are arranged like this one. We have to find the moment of inertia about this one. It is easy to find what is the moment of inertia of the rod about its center. So that is nothing but the center mass of the particle. We know the moment of inertia as m into L square by 12. Then we can change that moment of inertia into this axis by using the parallaxis theorem. Likewise, here the four contributors. So 4 into the parallaxis theorem will give the answer. The similar concept is here. Find the moment of inertia of the ring about AB. So the ring is take the form like this one. But that axis is parallel to its diameter. You know the central axis got the value as mr square. But here about the diameter it is mr square by 2, and hence the moment of inertia about AB take the value as m into r square by 2 plus mr square. You get the value as 3 by 2 mr square. We can move to the next question. A good question. The uniform solid block has capital M mass and its dimensions as A, B and C. Calculates its rotational inertia about an axis passing through one corner and perpendicular to the large face. So this is the axis under consideration. But we know the simple concept. If it is through the center of mass, the axis moment of inertia is as simple as m by 12 into a square plus b square. You know the value. But we need to find about one of the corner. So we can apply our parallaxis theorem. But we should know the perpendicular separation between both the axes, the central axis and the corner axis. So that can be easily find out by using this concept. So you get the answer. And here another good question. The diameter of each spherical shell is a capital R and mass m. They are joined by a light and massless rod. Calculate the moment of inertia of the system about x dash. So this is the axis. We have to find it. At first, the individual contributions of the moment of inertia about x-axis. So at first we have to find what is the moment of inertia of the spherical shell about its diameter. Simple. its radius is, diameter is r, and hence its radius become r by 2. But we have to find the moment of inertia of the second body about its diameter at first. Then we have to transfer it into x-axis by using the parallaxis theorem, and you get the answer. Then we are waiting a very, very good question. A thin uniform disk has a mass 9m and radius r. A disk of radius r by 3 is cut off. Find the moment of inertia of the remaining disk about an axis passing through O and perpendicular to the plane of the disk. The simple concept we have to follow is, we have to subtract that removed contribution from the total contribution. So at first we just the density are same for the removed one and also for the whole one. For the whole one, the mass is 9m, that division by area, it should be equal to the removed one that got the mass as say m dash, that division by its area. So you get the removed one got the mass as m. So what is the moment of inertia for that removed one? For the removed n, it is at a separation 2 by 3r. And at first find the moment of inertia of the removed part about its own axis, its a central axis. So simply mass into radius square division by 2. Good. Plus, by application of the parallaxis theorem, we can find the moment of inertia of the removed one about the O axis. It is very important. Then how we can find the remaining part? At first we can have to find what is the moment of inertia of the whole disk about O minus what is the moment of inertia of this removed one from O. You get the answer. Couple the pair of equal and opposite forces with the parallel lines of action are known as the couple. And keep in mind, it produces rotation without translation. The sigma f is equal to 0, but there is a non-zero value for torque. A mathematical concept to the moment of the couple, it is nothing but one of the force into the perpendicular separation. You should go thoroughly about the torque, angular momentum, and other dynamics variables. Very, very important for our exams. And keep in mind that the torque is nothing but the moment of the force. It is equal to the linear force into the perpendicular separation between the line of action and the axis of rotation. With a simple formula, as a tau is equal to r cross f. And there f into the perpendicular separation or r into the perpendicular force. It is a very important concept. The perpendicular force is the responsible one for rotation always. And keep in mind, if the particle is under anti-clockwise movement, the generated torque is always positive. If it is clockwise, then it is negative. Keep in mind the principle of moment, the rotational equilibrium. If the sigma f tau equal to 0, then we can arrive at this condition. When the object is in a rotational equilibrium, the algebraic sum of all the torque acting on it, it becomes a 0. So F1 by F2 take the value as d2 by d1. See, we can go with some problems relating torque. The body in figure is pivoted at O, and the two forces are acting on it. Say we can say it is a frictionless pivot. So because of the application of F1 and F2, we have to find the expression for the net torque acting on it. And if R1 is equal to 1.3 meter, R2 equal to 2.15 meter, F1 is equal to 4.2 Newton and F2 is equal to 4.9 Newton. If theta 1 is 90 degree and theta 2 is 60 degree, then what is the net torque about the pivot? And keep in mind that F1 will give an anti-clockwise torque to it, that is the positive value. We can easily find it is equal to plus. That is nothing but Rf1 sin theta 1. But that F2 will give what? A clockwise one, and hence it is minus R2 F2 sin theta. So the net torque is 1. So we can write easily as R1 F1 sin theta 1 minus R2 F2 sin theta 2. So you can just substitute the individual values given here. You get the answer. But the net value got the negative sign in the sense because of the two application of forces, it is under clockwise net motion. So that is a very important concept. And the next concept, a force F is equal to 5y plus 2j minus 5k acts on a particle whose position vector r equal to I minus 2j plus k. What is the torque about it? A simple concept, you get the answer. The likewise questions we can wait for angular momentum also. A uniform rod of 20 kg is hanging in a horizontal position with the help of two threads. It also supports a 40 kg mass. Then find the tensions developed in each thread. And we have to apply the two important concepts. If it is at rest, we can say the translatory equilibrium and also the rotatory equilibrium. So for translational motion, sigma Fi should equal to 0. The force along the vertical equal to 0. That we can say that T1 plus T2 should equal to 40 into 10. So that is a very important one. So also keep in mind the rod got a mass of 20, so 200 plus 400. So it should be equal to T1 plus T2. But for rotatory equilibrium, if the net torque should equal to 0, suppose you have to take the value about A, then the T1 contribution becomes 0. Then what is the contribution from 400? It will give a negative aspect because clockwise. So we can say that the force of 400 into the perpendicular separation as L by 4. But keep in mind clockwise and hence negative. And similarly 200 clockwise, so minus 200 into the separation as perpendicular separation as L by 2. But T2 will give a positive anti-clockwise movement. So plus T2 into L, that is equal to 0. And you get the value T2 equal to 200 Newton. By putting that value on this relation, you get the value of T1 also. A good concept is there. Find the minimum value of force for the block to topple about an edge. So keep in mind, because of the force F, suppose it tilt about the verge at the point O, at the edge O, then the normal is shifted along O likewise. Then you have to take the torque about O should be equal to 0. And here the two forces are here. One due to the wire at a separation A by 2 and N from O. And keep in mind it is from O, so there is no contribution. But F at a perpendicular separation of B. And hence we can say F into B should equal to the weight mg into A by 2. And you get the value for F minimum required. The angular momentum. So keep in mind the linear momentum into the perpendicular separation or equal to Rp sine theta. See the Newton's link with the rotatory concept. Conservation of angular momentum. If there is no external torque is acting on it, I omega is a constant. In the sense, keep in mind when I increases, omega should decrease. And keep in mind the time period it goes on increasing, and hence the kinetic energy should decrease. But keep in mind L is a constant. Similarly, if I decreases, omega should increase, T should decrease, and kinetic energy should increase. And keep in mind, for a planetary motion, the angular momentum is conserved. That means mvr should be a constant. That velocity is proportional to 1 by r. So in the elliptical orbit, that planet got maximum speed when it is minimum separation from the focus. And keep in mind the aerial velocity is a constant, and that is said to be L by 2m. It is a very important concept. And here the solid cylinder of mass 20 kilogram rotates about its axis with an angular speed 100 radian per second. The radius of the cylinder is 0.25 meter. Then what is the magnitude of the angular momentum of the cylinder about its axis? We know that L equal to I omega. It's a simple calculation. We are waiting a good question. The angular momentum L is given by L is equal to Rp. The variation of log L into log P is shown by We can use this concept. You could just apply. So it is the addition process. So multiplication becomes logarithm, addition in logarithm. So it becomes of the form y is equal to mx plus c with a positive y constant. So we can say 4 as the answer. Then a particle of mass m is projected with a velocity v, making an angle of 45 degree with the horizontal. The magnitude of the angular momentum of the particle about an axis when the particle is of maximum height h. So it is nothing but the linear momentum at the highest point into the perpendicular separation between the line of action and the axis. So that is nothing but the linear momentum at the highest point into the maximum height. What is the maximum height? It is v square sin square theta by 2g. And here theta is 45. So you get the value v square by 4g. And you know the highest point, the momentum is mass into the velocity there as v cos 45. You just multiplying, you get the answer. Another very good question is waiting. A particle of mass m is equal to 5 units is moving with a uniform speed v equal to 3 root 2 units in the xy plane along the line as y is equal to x plus 4. The magnitude of the angular momentum of the particle about the origin. A good concept, but we can employ the linear momentum into perpendicular separation. But here one line is line, so we have to draw that one. For that we can put value x is equal to 0. We get y equal to 4. When we put y equal to 0, you get x is equal to minus 4. So the two coordinates are 0, 4 and minus 4, 0. By using that 2 points, we can draw that line along which that particle moves. So we need the linear momentum there. So that is nothing but m into v. But we need the perpendicular separation. We can easily find it by using the sine 45 as the d division by the hypotenuse. By putting the value, you get the answer. A good application of a conservation of angular momentum. A thin circular ring of mass capital M and radius r rotates about an axis through its center and perpendicular to its plane with a constant angular velocity omega. 4 small spheres, each of mass m, are kept gently to the opposite ends of 2 mutually perpendicular diameters of the ring, then the new angular velocity of the ring. It is a very important concept, as I1 omega 1 should equal to I2 omega 2. And that before that there is only the ring is there, so mr square into omega. But diametrically opposite 4 small masses are there, so their moment of inertia become 4mr square plus m into r square, that for the ring, into omega 2. You can use the concept. You must go through the relevant, very important relations. In place of linear kinetic energy half m v square, here the term as half I omega square. And there that mass is replaced